Okay, welcome to the April Estes Part Group. This month we have Vishnu from Wiscube joining us. I'll give a quick intro here. Wisecube is a team of semantic data and AI professionals that build and maintain Orpheus, a biomedical semantic discovery platform designed to revolutionize the way pharma and biomedical researchers access and utilize biomedical information in their research. They're working with big and small organizations like Roche, IDRI, and others, providing rapid, reliable, and literature-backed insights to complex medical and biopharma problems, integrating the latest biomedical ontologies and AI models at scale to ensure users have access to the most current and comprehensive biomedical predictions and knowledge. So I will go ahead and put a link to Wisecube in the chat, but I will go ahead and hand it over to you, Vishnu. I'll keep an eye out for hands and flag them for you if you want to pause at any point and take those, but floor is yours.
Awesome. Thanks a lot, JT. Can everyone hear me?
Yep.
Awesome. All right, let me go and share my screen.
Looks good.
Awesome. Okay. All right. Okay. So I'll skip to this is our team. Brief introductions. I'm the founder and CEO of Wisecube. I have with me Alex, who's a principal data scientist, and also Seth, I believe he's also a data scientist working with Alex and a few others that I can't really see who else joined. And just to, a track record, JT sort of mentioned this. We work with, all kinds of companies, mostly biopharma and healthcare companies. Large and small. But let's get right into it. Talk about our platform. You guys, I'm preaching to the choir here when I talk about all of this stuff. We believe in representing knowledge as semantic data, right? So that's sort of our core of what we do. This is just an example of how we can extract triples from text data. Of course, this is all unnormalized triples like we do sort of then would map it, we can get into as much detail as you want. We have Alex here who can then sort of give us a deep dive with their questions and how we do this sort of automagical extraction of triples from unstructured data, unstructured and structured data, and what are some of the techniques we use. We can absolutely get into that rabbit hole for those of you who are interested. But once we extract these triples, we try to map them into our ontology, right? So I know I'm speaking to a room full of ontologists, so so the ontology, at least for the biomedical graph that we build, we looked at different ones, and we decided to go with this one that I'm showing you guys. You might be familiar with this, which is really a subset of what Wikidata uses to represent their information. And so there was this paper a while back by I've mentioned it here, by Wagmeister and a few others. So they actually did this exercise where they took a subset of Wikidata, and they were making the case like, hey, this could actually be a good enough ontology for biomedical research. And so we sort of decided to test that out. And so we were looking at different ontologies, and Alex, chime in here, is we looked at was it PubChem had its own ontology, and then BioLake,
PubChem has its own ontology. It's more than just like the chemistry stuff. They actually integrated a bunch of different things, and then we were also looking at Wikidata. We decided to go with Wikidata because the PubChem knowledge graph was much more like loosely connected. So essentially, there were connections between different knowledge graphs that you could have, but they weren't necessarily all on the same manner of representation. Wikidata also had another benefit, which is like, although we're focused on biomedical, if we did want to do something in another domain, we could similarly use Wikidata's because of how general it is. We could use their we could use that ontology for other domains as well.
Yeah. just looking at the questions, so there's a couple of questions on how to handle errors and extraction errors and out of scope information. I think there is a section where we talk about, there's a product we have like called Pythia that actually tries to detect factual errors and so on. And maybe if you can hold on to that question, we'll definitely try to address that. But there's another question that talks about like, hey, what happens when your current ontology is lacking in depth or breadth, and how do you deal with those kind of scenarios? And yes, we do run into that. Oftentimes we try to, bring in data that it's not immediately, easily sort of representable in our current ontology, and we would have to add new entity types or new relationship types to sort of extend it. Hey, Alex, you don't know if you want to add some color there as well, but yeah.
Yeah, so I think I think a lot of these questions are good. Yeah, they're related to like a similar thing. So if we have because the first one you mentioned was about missing or information and correct interpretations. What we generally are trying to do is I would rather get less information from a document or from whatever we're extracting from than get wrong information. So we try and err on the side of only getting things that match with our schema. We also, because we're using RDF graphs, whenever we are, because we have the two sources of data that's going to go into the knowledge graph. We have obviously stuff we extract from documents and stuff that comes from structured data. Stuff from structured data is going to be a little bit more trustworthy after a fashion, as in like we don't need to worry that we misinterpreted what's there. The interpretation is in the documentation of the data. So we keep things that are extracted via a model, like the ones extracted from text. We keep those stored separately, so that there's our sort of an understanding to the user, like, hey, this is a model. There could be some errors there.
Yeah. And then how do we deal with like when the ontology needs to be extended, right? So
yeah, so that is, so when we're extracting triples, we map things, and if there's something that we're unable to map automatically, we will review it manually and then decide whether, like, maybe our mapping logic is wrong, or maybe we are legitimately missing that representation. There was one situation we ran into that, which was actually sort of one outside of the biomedical domain, where we were missing a lot of things that we needed to represent the data, and I augmented it with stuff from schema.org at that point, because most of what we needed to represent was stuff that wasn't too weird or arcane, but it wasn't in Wikidata, because there's a little more.
So stuff like I'm thinking more recently, like we're trying to bring in genetic data into our graph, and it's not that our graph doesn't already have genetic data, it has lots of sequences and genetic information, but the granularity of data that we're trying to bring in is not really represented in our current ontology very easily. And so that's another example of where we're like, okay, this is a different level of granularity than what our ontology currently supports, and so how do we extend it? And that's often with those kinds of discussions. We do have an I don't know if we can call Tiago an ontologist, but he's the closest we've got to an ontologist in our team. He's very familiar with the Wikidata ontology itself. He works with their community, and so he's able to sort of make recommendations if we're going to try to extend Wikidata in any ways, so it can actually benefit the community as well. So that's the beauty of like sort of using an open standard like Wikidata, which is like, hey, sometimes when we try to bring in certain data sets and we're like, actually Wikidata's, this ontology doesn't really work well. It would be cool if, we could extend this, and he would actually make recommendations back to the community, and sometimes they do get accepted. And so we're also contributing back into the community as well. And so that's sort of, it is a lengthier process. Sometimes we would just do it internally and then let the process work itself. But it is something that we would often we have encountered in the past, and it's good to have somebody on the inside who can also help us with those kind of discussions. So yeah, moving on. So we bring all of this data in, and sort of like we over 100 data sets, not just ones from the Wikidata, and so we build this massive knowledge graph. It's like billions of facts. tens of thousands of relationships. We also bring the clinical trials data in, and and all the research article data. We extract around like 250 million facts from that, and so all of this, and we throw it all into this giant graph, which is great. But so in the world of like generative AI and LLMs, where you have these like massive models that people are confusing with source of truth and verified facts, we think more than ever before, having a verified source of facts that are ontologically represented in this way is more important than ever before, right? So if you do not know what your facts are, then everything is a hallucination, right? And so that is sort of our primary premise that we operate on, which is that AI is great, but how do you know what reality is if you don't have a frame of reference, right? So and so that's sort of what our platform tries to do, is like, hey, build your frame of reference, right? You do your AI, absolutely, but first, sort of bring out all your data, normalize it, extract your semantic triples, build the graph, and we've demonstrated with the graph we've already built, but we can do this with proprietary data as well, and we've done it, and so you build the graph. And not only do you stop there, now, of course, when you build a graph, it's immediate value, as you guys know. Okay, now you can do querying, you can use it for AI models, you can do all this, you can do it for fact checking. There's a whole bunch of value that just immediately it adds. But what we did is, in the literature, they call this like graph completion, right? So we trained a network model on top of the graph. And this is something that, not a lot of people do, is like, hey, so what we did is we trained using a link prediction model, basically a network learning model that can try to learn these signals that exist between the connections, right? And so it tries to learn that, hey, this entity is connected to these other, this disease is connected to these drugs and these sequence variants and these things. And there's information in those relationships. And it tries to learn that and represent that as a high dimensional vector. So that's the embedding model that we actually train on our graph. And why does this matter? Because once we've trained that embedding model, then we can start using that to try to make predictions between entities that are not even related, any two entities in the graph, right? So then we can say, hey, the simplest example would be like drug repurposing. Hey, find a drug that already exists that can potentially affect this disease. In fact, we did this for Providence Healthcare, like they were looking for Alzheimer's, and they were like, hey, let's run a drug repurposing exercise. Great, we use that model, right? And then the more complicated one, I'll talk about in a second, is one we did with Roche, where we were trying to predict biomarkers for a specific type of cancer, right? And so the list of use cases just go on and on and on, because now you have all of the signal that you have and all of the learnings from this massive knowledge graph sort of distilled into this sort of network learning embedding model that you can then use to build other sort of application-specific AI models or purpose-built applications, right? You can still do all the things you do, but like now you've distilled all those learnings into this sort of network learning model, right? And that's sort of what we've done, and we've shown that this can actually work in a lot of cases better than just being able to build a one-off siloed application/AI model, right? So this whole idea that you guys are talking data-centric sort of journey, this sort of is in line, we think, with that kind of an approach, right? So focus on building your data representation, normalizing your data, figuring out your ontology, and then don't stop there. Train your network learning model on top, and then go and do all this AI stuff that you're going to do, and then you're going to get way more value. And by the way, you don't need the same level of labeled data that you would need if you had just done a siloed approach, right? And Alex, I don't know if you want to, maybe we'll talk through some of these examples of how this we actually ended up using this. But I want to take a moment, like just get through some questions that's around this before we go into the specific examples of how we actually did this for our customers.
Doug.
I'm intrigued by your link prediction slide there, because it's my understanding that the problem of native graph embedding has really not been solved yet. Are you going to talk a little bit about in detail what kind of model you use to embed graph nodes?
Yeah, no, we can definitely get into the details. We tried a few different algorithms, and we'll talk about the specific use case where we did with Roche, and maybe Alex, we can get into some of those details. In fact, the study, the results we had with Roche, we are going to publish that as a peer-reviewed research article. It should be coming out sometime this year. So, but yes, absolutely glad to talk about that. Yeah.
Good, thanks.
Some of these, features, you guys are already familiar with these, but let's get into, I'm going to skip through the RAG portion. By the way, this is just, okay, now you've built this graph and now you can use it for querying. Everybody talks about RAG these days, retrieval augmented generation for generative AI. Oh, turns out you can actually do RAG on graphs, right? And we've actually done this. We built a pipeline that can take in natural language questions and convert them to Sparkle queries. And, Alex and Seth is here who, helped build this. And so it's sort of, I don't know, Alex or Seth, like if you want to give some color on this and some of this pipeline. In fact, there's a whole webinar that we did, and we're also trying to get this published as a research article as well. So yeah, go ahead.
Yeah. Do you want to go to the next slide? So yeah, a large part of this had to do with like how we wanted to so we were looking at other people who tried to solve this previously, and a lot of their techniques were very specialized to not necessarily the structure of their ontology, but literally sort of like the string representation of their ontology. Like, for example, there was one that was based off of Freebase, and it really relied on the fact that the URIs used in the Freebase graph were composed of mostly English words and very few IDs. But we didn't have that luxury. Wikidata ultimately has these like IDs, and if we try and like use an LLM to do that, we'd have to have the LLM learn all of the IDs, and that would be a lot of fine-tuning, terrible approach. So the real trick came with decomposing the problem into two steps. One is converting converting or extracting from the text the unnormalized triples, or natural language triples, as we call them. And that's what the examples you saw earlier in the slides, where it's like disease X is treated by drug B, right? So once you do that, then you just need to work on the normalization aspect, which we do by taking the data that we have from the graph, so all the different names of the relationships and the entities, and mapping there. So we have a set of heuristics, as you know, and we're looking at other methods, but yeah, for extracting. So we've actually had pretty good performance so far on our test sets. Correct me if I'm wrong, Seth, but I believe that we're getting like 80% accuracy in terms of measuring to make sure we get the correct results back. If we get the correct results back, the query likely is correct. But yeah, I believe it's like 80%.
Yeah. So Alex, do you want to talk about the intermediate representation? The trick is like, we convert these natural language queries to this sort of intermediate representation,
yes,
which is almost like set builder notation that you're seeing here.
Yeah.
And then, go ahead.
If anyone here is familiar with like computational semantics or stuff like that, or representation of semantics in like linguistics, that representing the semantics in the language using the sort of set-like notation is a pretty classic linguistic thing in the subfield of semantics. And so really what we do is that we're taking the natural language, representing it in the set builder notation. So representing it as these statements, which happen to be very similar to what you use in Sparkle. Sparkle is the query language we're using because we're using an RDF graph. And so, when you query in Sparkle, the primary work of what you're doing is all in the where clause. And that's really just like a series of constraints that exist there. And when we extract these triples, it serves as those constraints. So all that needs to be done is that normalization step. So this intermediate representation was really like the key to getting a lot of progress, and also of divorcing the extraction from the specific ontology. So It's true you would probably need to like do a lot of tuning if you switch to like a completely different graph, but you wouldn't need to like learn all of these IDs that you see in the query and in the lower part.
Yep. So yeah, go ahead, sir. Yeah.
I was just going to say that, like, with the modular prompting, you kind of need to do even less to switch to a new graph. You just need to, provide a sufficient amount of examples, and then this whole pipeline is graph agnostic.
Yeah, so modular prompting is where, because we treat the extraction process as a few shot problem for the LLM. So basically, we're in the prompt we're sending, we're giving some examples. And so the idea with modular prompting is that you have a collection of examples that you first retrieve the relevant examples for your query. Then that will help generate the triples from the text.
Doug, you have your hand raised. Was there a question?
Yeah. Could you go back to that previous? Yeah, there you go. So I really like your idea here of taking well, and I don't know whether this is just illustrated for the slide or whether this is kind of the actual process that you went into, but of using essentially the where clause and the triple patterns in the where clause to define, in essence, the path to the data that you're looking for. I'm interested though, when I see in your structured query the set builder notation, things like genetic variant of and EGFR, do those come from the actual nodes below they're a label of some kind on, let's say, WDT P3433 has a label that is genetic variant of, and that's how we can translate between these two views?
Exactly.
Yep.
So that's why when we decompose into two parts. So the extraction produces that set builder notation up there. So let's say that in the query they were looking for, they're asking for, it would be genetic variants of EGFR that are positive predictors for erlotinib and lapatinib. So excuse me, that query is decomposed into this. So obviously it's a question, so that's where the X is coming in. And then we have the gene and the two drugs there. In the knowledge graph, there's the preferred name and a set of aliases, and then that's what we're using to match the thing extracted from the question to those particular entities.
Yeah. So Doug, think about it as almost like a compilation process, right? You have your intermediate language where you're at the symbolic level. So the set builder notation tries to stay at the symbolic level with aliases, right? And then there's a linker, if you're familiar with compiler design, that comes in and says, hey, I'm actually going to put in actual references to memory and IDs and all these things. That's what we need to do before we can sort of materialize the set builder notation into a specific Sparkle query, because the Sparkle query doesn't understand aliases and handles, right? It needs specific IDs for predicates, needs specific IDs for entities, and so on. Otherwise, it's just going to be I don't know what you're asking me to do, right? And so there's almost a step after this that takes the set builder notation and then replaces it with the specific IDs of the predicates and entities.
Yeah, I would also just kind of add that there's a, not shown here, but there's a pivot point in the middle. So the set builder, we're trying to kind of keep away from the Sparkle, because again, we'd have to train the LLM on all of these different IDs. So it's just transforming anything it finds in the natural language question into this triple structure. And then after we have this triple structure, we can pivot to the Sparkle stuff by getting, mapping aliases to IDs and such.
And that's the entity linking, right? They call it entity linking in the NLP world, but yeah. So,
but is your SBN representation being created as an output of the LLM, or is that handwritten?
It's an output. Yeah.
The LLM is creating it, but
the LLM is creating your SBN. Okay.
Yeah.
Right.
Yep.
All right. Interesting.
Yep. Yeah. We actually we're actually in the process of releasing this as one of the features in our API, where people can just submit natural language queries and query the graph without having to learn Sparkle. We all love graphs and Sparkle and whatnot, but we can't really say the same about the rest of the world. So this is a way to sort of reduce that learning curve, right? So Anyway, we did a whole webinar on this. I'll share this deck with you guys, and then so you'll have access to all these links as well. So you can there's a whole deep dive that Seth and Alex did on this whole thing as well. So let me skip that. So the next, so that's sort of the whole graph rag thing use case that I want to sort of go through. But I know you guys are also, we talked about link prediction briefly. So I want to spend some time talking about like how we use that discovery and like try to get back to that. But before that, any other questions on the graph rag and the natural language to Sparkle query generation stuff before I move on? Yeah. Nope. All right, let's keep going. Drug discovery, it's a, it's a very, it's obviously a difficult domain. There's lots of different fragmented data problems. It's complex biomedical interactions, lots of black box models. And so we saw this and we're like, hey, you know what would be great here? Knowledge graphs. And so we started building one, the one I was talking about. And then we realized, hey, now that we've got this, we could even do better, and just give access to the data to people, but we can actually start making predictions. And so the whole idea of link prediction, as I said, is like, hey, the model tries to learn from the existing edges, right? So it's like looks at all the edges and all the entities that are connected, and then tries to come up with a vector representation for each entity. And there's different algorithms to try to do this. The simplistic ones, what they do is they try to ignore the kind of relationship that exists, so the predicate types. So it just says, hey, EGFR is connected to drug A. I don't care how it's connected. I'm just going to account for that, and then I'm going to try to see what else it should be connected to. And those are the really simple ones, like the Jacquard similarity ones, or there's a few others, right? That do that, and they're useful to a certain extent, but for the kinds of problems that we were looking at, like biomarker prediction or drug repurposing, we have in our graph, our ontology, we have over 10,000 relationship types. So there's a reason why there's so much, predicate types in our ontology, because those all matter, right? Especially in this domain. And so we just simply can't ignore those. And so we were looking for an algorithm that actually would take that into consideration when trying to learn a vector embedding for each entity in the graph, right? So, and Alex, do you want to maybe just talk about some of the algorithms we look through and how they try to compute these learn embeddings and how they try to learn? I don't think we have a slide here, but maybe just talk through it.
Yeah. So earlier, I don't recall who said, but said that sort of the node embeddings wasn't a solved issue, and yes, that may be the case. But I guess the way we were approaching is that it doesn't necessarily need to be a solved issue in order to get the benefit that we're looking for. If we go back to the thing okay, well, what are embeddings? Embeddings are this higher level representation of the data you're putting into your neural network. And what that higher level representation is, even if it's not necessarily easily explainable to a human, it does compress a lot of information into that vector. So the thing is, we just want to learn this vector that gives a lot of information to the node that can then be used to train a model. But towards what Vish was saying earlier, that it was like classical machine learning, you have to do a lot of feature work, and that requires both specialists in the domain and also requires a lot of time and effort to do so. And even then, it's often difficult to get past if you plateau in your performance, the featurization work can sometimes be a very time-consuming process. But with these higher level representations, you tend to get a lot of different information sort of all baked into that embedding. So some of the different algorithms we use. So Vish was mentioning earlier, we did try looking at deep walk initially. Obviously, that doesn't have the predicates, so that wasn't good enough. So then we started looking at some of the I guess classic link prediction embedding algorithms with trans-EL2 and complex. Those are the two main ones we've experimented with. So with trans-EL2, it tries to represent the vectors such that the head vector plus the relationship vector should should approximate the tail vector. That's the sort of the equation we're trying to learn, if I'm recalling it correctly.
Yeah.
And of course, that sort of like makes sense in a very sort of like linear algebra type way, but there's of course an inherent problem with that. It doesn't allow you to learn like multiple edges between nodes. It assumes that every connection between for a given head, it has an R relationship to just one T, and that's the only way it relates to T. And of course, that's assuming way too simple of a structure. Now, from our experience, the information that is put into the node vector is still quite good and quite usable. So although it's not really good for its intended task of link prediction, it does provide good features. But complex, which is it allows for to predict multiple connections, and that one is I'm trying to remember. So I don't remember the exact sort of like the inspiration behind complex, but those vectors we find they perform better for the baseline link prediction task. But there's not a significant difference in how there's features for the machine learning problems. Yes. Do we have anything that talks about the? I guess this is one for biomarker. Do you have the?
No, this basically talks about our. So what we did, I'll just give some preamble on what we did for Roche. So when we built this graph and we sort of said, okay, can we try to use this massive graph that we built and try to do something with it, maybe a predictive task like predicting cancer biomarkers, looking at it for specific kinds of cancer and looking at specific kinds of sequence variants. So that was sort of like the task we were trying to take on. And we said, okay, you can train a link prediction model that can look at these kinds of sequence variants and see which ones could be biomarkers, and then try to validate the ones we predict using some industry standard result set, right? In this case, that gold standard was CIVIC. For those of you familiar with CIVIC, it's a cancer biomarker data set that's like, it's sort of hand curated with, based on different levels of evidence that you can potentially have for biomarkers. And it's sort of considered the gold standard for cancer related biomarkers, right? And so the whole idea was like, okay, we're going to train this graph, or train this model, go after these sequence variants and see if we can find any of these sequence variants that could be potential biomarkers, and see if any of them actually show up in CIVIC, right? And that's sort of like the experiment we tried running, and I'll let like Alex walk through how we did this. It's obviously a complex workflow, no pun intended. And then we come up with these predictions, and this is all written up in this paper that we're going to jointly publish with Roche. And hopefully will come out soon, sometime this year. Roche moves really slowly. Their legal team takes a long time to get through stuff. But anyway, we're finally here. It's submitted. It's going through the process. And Alex, take it away. Just walk us through this process.
Yeah. So the first part is this is also like sort of covering our experiments between TransDL2 and complex, but so we mark as the first step, which is like actually building those embeddings. I think there's some of the numbers were messed up here. Oh no, I'm wrong. No, it's fine. So then the next thing we want to do is when you're building complex or TransDL2, it's trying to optimize across all predicates, so the whole graph. It's trying to learn a generally good link predictor. First for that, the question, Martin Romaker. I don't think we met him. Yeah, it wasn't with his group, as far as I know.
We were working with the Roche Diagnostics group. They're based out of Foster City. So our champion there was Antonetta. Her name is Antonetta Vladimova. I can't pronounce her last name. Yeah.
So those two embedding models, they're trying to do link predictions across everything. But the two specific predicates we're looking at is positive therapeutic indicator. So basically, the presence of this sequence variant, this is variant in the gene, is an indicator that the drug will have a positive effect on the patient, and then negative therapeutic indicator. So we wanted to predict those two, but they were relatively small in the graph. So although these models did perform well in general link prediction, they didn't perform well enough for what we wanted to do with these specific predicates. So what we want to do now is train that second level model. This is where sort of that information content that's inherently in the vectors becomes valuable. So what we did is we found all the positive examples. We generated synthetic negatives similar to how it's done in the embedding models, where you just sort of you pick one of the triples and you replace it with a random incorrect thing. So that produces our training data. We then trained two, or for each of the embedding models, we trained random forest classifiers, which we are not using actually as classifiers. As I was very clear, we're using them as rankers, because the truth is that we're not really able to predict any sort of like probability of something being a biomarker, but we can, if what we're doing does have information, and it does have some information value, we can help prioritize what is looked for. So we build those models, we get the predictions, but another important part is we need to find a bunch of unlabeled data to, which would be sort of the whole point of like what would be provided to the researchers for them to look through. And so from that part is where we we take all the positive examples, so the positive pair, so a sequence variant and a drug, and we find alternate paths between them. Then we find other pairs that can be that are also found through these alternate paths. So these would sort of be our candidates, and that's our unlabeled data. Obviously, that unlabeled data at this point can't be used for training because we can't verify anything about it. But what we do is we rank that data and provide it to them, and we check some of that data in Civic, and we were able to, I believe it was like was it like I'm trying to remember the ratio of what we did over like the random selection. I think it was like 10 times over random or something. We definitely did much better than,
there's definitely
random
signal there.
ranking.
Yeah, and remember, even though we say this unlabeled data and training data, there was no human labeling that was done before the fact. We started with the graph. That's it, right? It's all like unlabeled data, in that classical sense. Nobody's gone in there and saying, hey, this is the right data and this is not, and didn't spend any time annotating any of this, right? Which is typically what you would have to do for a deep learning model of any kind. You would have to spend a lot of time where humans go in and annotate and label this and produce lots and lots, gobs and gobs of labeled data, right? Before you can train a deep learning model, which none of that we actually did as part of this process. We literally like took data from the graph. All we did is like, hey, these paths, they seem like good paths, let's use them. And then start this whole workflow was sort of built off that. Yeah, Doug, you have your hand raised.
So is the unlabeled data unstructured data as well, or are these little slices of triples?
They're all just triples, because everything is a triples. Yeah, at this point, there's no unstructured. It's all really just the graph is the source for the whole pipeline.
Okay, so so this has not been run through the embedders. It's just
the embedding has already been trained, right? So at this point, we've already done like the training on the entire graph, and the embeddings have been generated already. And so this is like a exercise that we do after we've learned the embeddings from the entire graph. And then we're saying, hey, can we go find these cancer biomarkers around this small neighborhood of the graph and try to predict what's happening there? So that's typically your workflow. So you have your giant graph, you learn the embeddings across your entire giant graph, and then once you've learned those embeddings, then you go and saying, here, what is the specific drug discovery problem that I'm going to try to solve in my corner of the graph, and then go do this kind of thing, right? So
okay, yeah, interesting, good, cool.
Yeah, any questions? I guess we could, Alex, I don't know if you had any thoughts, but like this, we did this similar thing as well for like, Providence, where they had a different problem. Theirs was like more like drug repurposing, which in some ways it's much simpler, but the same idea. You have a graph, and then you like train the embedding model, and then their problem was like, hey, I want to go after this specific pathway, the CDK5 P25 pathway, and I want to find which drugs actually try to inhibit that, because we think our research indicates that if you inhibit this pathway and this enzyme combination, it actually helps, prevents Alzheimer's from like developing. That was their research, and said, okay, we'll go and find like, and we ran the same exercise, and this time instead of looking for sequence variants, we looked at drug pathways, right? And so drug to disease, and what are the things in between, and then we found all those. Of course, with the added wrinkle, remember, Alzheimer's is a neurological disease. So even though our link prediction model might say, hey, these actually sound like good things, but not every one of those drugs might enter your blood-brain barrier. And so we actually have ADMET models like that we've trained that can give each drug a score and saying, hey, what can it actually pass through the brain? And we were able to filter it down and then, and do all that. I don't know, Alex, did you want to add your color?
I think one important part about that pathway is that when they came to us, they said that the reason why they needed some approach like ours is because they had only like 2 or 3 examples of drugs that target that pathway. And there's essentially, for them, there's almost no research on even candidates. And so what they were looking at that time was like, okay, so we're just going to have to like make some educated guesses and then just brute force check everything with no idea of how to prioritize. Because there was just not nearly enough data to do any other sort of learning. And again, yeah, so this becomes an issue of like the information that's in the graph maybe isn't enough to like automatically like completely solve the problem, but it can help prioritize. And I think this is true of a lot of sort of what Vishnu was saying with a lot of like classical machine learning stuff. If you can frame that machine learning task into a question in the graph, like, oh, are these 2 things connected, or does this have that property? If you can frame it like that, you can then use the what we've shown to be like information rich vectors as a baseline set of features. So it can help with machine learning tasks that are otherwise unfeasible.
Right. Which is why I think it's like, we think it's a foundational model, right? Which is like embedding model, similar for those of you who are familiar with BERT and other sort of foundational text embeddings. So think of, this embedding is sort of a foundational graph embedding, right? So that we've created on top of the graph, right? So, yeah. I'm gonna skip through this in the interest of time. There's one more thing I did want to talk about, especially with relevance to all the generative AI that's happening, and there's a question about errors and how knowledge graphs can help with that, right? And so we're building this product, and actually we're piloting this with Roche as well in a different group around clinical decision support. What they're doing is they're actually building a clinical decision support system using an LLM. They're taking all these patient notes and like whatnot, and they're trying to summarize that and feed into an LLM using a RAG system, and then show the summaries to physicians so they can actually, take care decisions based on those LLM generated summaries. And if you're not scared already, you should be, right? Because we all know LLMs are notorious for hallucinating. And the worst part is, I think the industry, because they're so hyped about this technology, they're sort of rushing in with, without a lot of forethought and a lot of guardrails built in. And I just hope it doesn't really, end up becoming something massive. But we're already starting to see these sort of embarrassments and sort of big blowups happening in the news. And there is, LLMs are getting better, but it's never going to be the point where it's not, there's going to be a 0% hallucination rate. It's just because just the way they're built to work, they work because they can hallucinate. So it's almost like a feature. If you listen to like LeCun and all these guys talk about LLMs, you realize that's what it does. It doesn't memorize, it hallucinates, right? And sometimes, most times, the hallucinations match reality, but every now and then it'll just go off and say something that sounds so convincing, but it's not factually accurate, right? And the question becomes like, how can you tell, right? And so that's sort of one of the problems that has really interested us in the recent past. And so we're working on this and trying to build an application that can potentially detect these factual inaccuracies that LLMs generate, and in different contexts that they're being used, right? So if you're familiar with LLMs, there's like the zero context, which is the worst way to use it. Just ask a question and it's just going to hallucinate some response. But nobody really uses it anymore like that. Most people use it in either the noisy context, the accurate context. Noisy context is the typical RAG use case. They feed it a bunch of documents, and then it uses those documents to generate a response based on the question. And then the accurate context is where like there's just usually a summarization of a document or information extraction or parsing or things like that, where they just feed it one document and then expect a response of some kind. So both of these contexts, we want to support all of these contexts, and we were looking at a way to sort of use this idea of semantic triple extraction. So what if we were able to extract triples from both the response that the LLM generates and the reference, and then we compared those two sets of claims or triple sets, and to see what percentages match and what percentage of triples that we extract actually contradict with each other. And then which ones we're not able to say anything about, right? Where the response contains some triples that we're not able to validate in the reference. And so it's a very simple idea. And so we can do this, and we can do this with high accuracy, then we can at least try to quantify what is the potential, upper bound of hallucinations in your given AI application, right? And so that's basically what our system tries to do. Just like what I just described is like, hey, take the response, extract the triples. Now you have a set of triples. Take the reference that you provide the LLM, do the same thing, and then we check again. So we use different kinds of checkers. Some of them do SOMs, some of them don't. So there's a whole complicated system. And then finally, we produce this sort of report that gives you an overall metric of how accurate, from a correctness perspective, your application is. So we're actually doing this with another team in Roche, and we're providing an audit report for them. But where it really becomes interesting is like, you can do this on a continuous monitoring basis, where like, yeah, you can do this during development time, that's great. But then you can put this kind of system in your runtime, and we can constantly monitor like what's happening. Let's say OpenAI decides to do some funky things and starts hallucinating much higher than it normally would because they changed something on their end. Would you even be able to detect that in real time and react to that, right? And the answer to most applications that are built on OpenAI right now is no. They absolutely wouldn't even recognize that till somebody starts complaining, right?
That actually happened a few weeks ago.
Yeah, I'm not surprised.
Yeah, remember there's this like bug or some issue where OpenAI was like producing like sort of nonsense, and they sort of found out about it because like a bunch of other applications, like people who are using those were getting affected, and then they were able to fix it. I think,
Dave, you have your hand raised. Good. Yeah.
Yeah. So would you say these missing facts are still hallucinations, but they're benign? They haven't been proven to be wrong yet?
Yeah, exactly. They haven't been proven to be hallucinations yet. So we sort of reserve judgment on those. And by the way, that's where the knowledge graph can come in. Like if we did have a fact base and we say, look, we can take these blue ones and we see which ones were actually matching or contradictions. And so ideally we want to eliminate all the blue ones, the yellow ones, and saying, hey, all the yellow neutrals either are green or red, right? Yeah. You're exactly right. So
sort of like open world, Yeah. Anybody can say anything about anything, but unless it's wrong.
Right. Yeah, you're right. So and so we came up with these metrics based on these three factors, right? Like, hey, and Alex was the one, I'd say we, but it's Alex. And is the entailments, contradictions, and reliability, right? So those are the three factors we look at as part of the overall accuracy. Alex, do you want to just briefly talk about this? Yeah.
So again, remember here, like we have sort of three sets. We have like the input, the reference document, which is going to have a set of triples. We have the generated text, which produces the response triples, and then we have this external source of triples as well, like the knowledge graph. So entailment is the proportion of the response triples that are supported by the reference triples. Contradiction the proportion of response triples that are refuted by the reference triples, and reliability is that sort of the those other ones that aren't supported or refuted by the reference that's in the response.
The yellow
Yeah,
ones, right?
Yeah. Blue here is actually the ones in the reference that weren't used in the generation of the response. So in this case, both of those are sort of like triples that are unverified. But the yellow is where like the hallucinations would be. Blue would just be like that's the hallucinations people have. So yellow is the where the hallucinations are. And what you want to do is you want to try and identify like, okay, what is the quality of these neutrals is sort of what they're called in like in the field, but these sort of like unverified things that are in the response. So this actually is important again for like other stories that came up. Like there was an airline where their chatbot gave a policy to a customer for a bereavement policy. Basically, they would get a refund on some of their ticket because it was for a flight towards a family member funeral.
Yeah, it's Air Canada. Yeah.
Yeah, and the court forced them to honor that what their LLM said. And then there's one we don't even have up there yet that happened a few days ago. In New York, they have their own chatbot, and it recommends for restaurant managers to take tips, or for landlords to discriminate based on source of income. So like it recommends people to break laws, and that's because like what it's producing, there's no validation. If you had, let's say, for the New York example, if you had a knowledge graph about like things related to law, you could check that against it before returning that to the user. So you're not recommending that that a landlord break the law.
Yeah.
So
you want to talk about the task specific? I know we're up against time here, like 5 minutes left, so probably wrap up. Yeah.
So the metrics we were just talking about, they're sort of like task agnostic. There's no concept of like, well, what are relevant facts? Like, for example, in the clinical setting, we're looking at patient summaries, and maybe they're interested in understanding the staging and histology of the cancer, and they're not as interested in like, medical history. Well, if we want to make sure that that we're measuring what they're specifically interested in, we say, okay, so all the predicates that are related to histology and drug staging, those are the ones that are going to have a higher relevancy score, and we can like discount all the rest so that we can make it more specific to the task at hand. And there's a number of other like task specific ones, like in summarization, you want to make sure you have conciseness as well. So you want to do something like, well, what's the in the side, what's the ratio of valuable triples to the size of the response. And then I guess sort of the final metric here is, well, how do we know we have a ruler now that says 12 inches, but how do we know it's 12 inches? Maybe it's 14, maybe it's 10. So how do we measure the ruler? So what we do is we come up with this case of, if we give the same document as both reference and response, we would expect to see 100% entailment, 0 contradictions, even 0 neutrals, even though we don't measure for those because that's not as much of a concern in this situation. And then we basically are just measuring what is the amount of error. So how much contradictions obviously increase that error metric, entailments decrease it. And so we use that to sort of measure the measuring stick.
Yep. Anyway, I'll skip through these, but yeah, so the idea is then, hey, you can build this sort of continuous monitoring system, which can plug into any AI application. They could use any LLM, they could, however they build it. And so we would act as this sort of like almost, hey, reliability monitoring solution where it could be configured to alert and so on. And over time, our plan is to sort of produce more and more signals, like not just correctness and hallucination, but like fairness and like bias and all these other things that they could also see how well your AI application is doing. And this is where the knowledge graph comes in, right? So once you have your knowledge base built into the knowledge graph, then all of these claims that we extract, then we can just validate against and check those triples and saying, hey, does your policy actually say this? Should you actually be giving refunds? And that kind of stuff, right? And so that would obviously be something we could, we would help our customers sort of build up that beforehand. And yeah, before we descend. Anyway, so I know we're at time. There's more case studies. Like, by the way, we've also done this kind of work with other domains, not just, I know we talked a lot about life sciences, but we have worked with the e-commerce and retail domain. This was like industrial chemicals retailer we worked with to build a knowledge graph there. It's sort of, we think of it as a, slightly related but different domain. We've worked with Qualtrics to build like a product knowledge graph. So it's even though like we are very much life science focused, this methodology on our platform can extend to other domains. And we offer our whole thing through a sort of obviously platform that can be deployed on customer premises and at their AWS account. We also have a hosted offering through an API and whatnot. That's us. I want to leave a minute. We got a lot of questions, so but just want to wrap up before we run out of time. So
yeah. Real quick, Vishnu, could you email me this deck when we finish, and then when I send out the recording from today, I'll include this so everybody's got it for reference.
Yeah, and I realize I threw a lot of stuff at you guys, but I just wanted to show a whole breadth of the kinds of things and applications that we built using this technology. So
cool. Any last thoughts or questions? Okay, well, this was excellent. Thank you very much, Vishnu, and everybody else over there. We really appreciate it. And we'll get the recording out today, and I'll include Vishnu's email if anybody wants to get in touch for some further discussion. So
thanks, everyone.
Awesome. Thanks all.
Yeah.
Thank you.